Alright, so this is problem 39 from chapter 7. And the problem says, a block with a mass of 0.5 kilograms is forced against a horizontal spring of negligible mass, compressing the spring a distance of 0.2 meters. Sorry, not 20 meters, 0.2 meters. When released, the block moves on a horizontal tabletop for 1 meter before coming to rest. The force constant K is equal to 100 newtons per meter. What is the coefficient of kinetic friction between the block and the table? So, we've got a tabletop with a spring attached to a block that gets compressed from equilibrium a distance of 0.2 meters. The block then travels a distance of 1 meter once it's released. We know that the mass of the block is equal to 0.5 kilograms. We know that the spring constant is equal to 100 newtons per meter, and it wants us to find the coefficient of kinetic friction between the block and the table. And that's what we're looking for. That's about a question mark. So, we can use the work energy theorem. We know that the force from the spring is going to be a conservative force. So it's going to be 1/2 K times the distance that it's compressed squared plus, and then we also know that there's a frictional force because we're looking for the coefficient of friction, and we know that friction is a non-conservative force, so we know that that's going to be the integral from over the distance that the block has traveled, so from 0 to 1 meters, of the force of kinetic friction times dx, and that is going to be equal to the energy in the spring after, but because we know that the block is released and the spring will go back to equilibrium, this term is going to go to 0. So we then have 1/2 K, the distance that the spring is compressed squared, plus, so we know that the force of friction, of kinetic friction, is going to be equal to the coefficient of kinetic friction times the mass times gravity times the angle. Because it's on a horizontal plane and the force is in the plane of gravity, we know that the normal force is going to be acting perpendicular, and so we don't really need this term. So we can then substitute this up here for K, and since none of those are dependent on distance, they'll all come out of the integral. So you have coefficient of kinetic friction times mass times the gravity times the integral from 0 to 1 dx is equal to 0, which is then 1/2 K x squared plus coefficient of kinetic friction times mass times gravity times 1 minus 0, because that's x evaluated from 0 to 1 because there was no x in the integral. It's going to be equal to 0. This is just going to be equal to 1. So then we can start to solve for the coefficient of kinetic friction. So coefficient of kinetic friction times mass times gravity is going to be equal to minus 1/2 spring constant times distance compressed squared. We can then divide by the mass and gravity. So coefficient of kinetic friction is going to be equal to -1/2 kx squared divided by mass times gravity. And then we'll also plug in all of our variables, so it's going to be -1/2 100, because that's the coefficient of kinetic friction, times the distance that the spring is compressed, 0.2 meters, squared, divided by our mass, 0.5 times 9.8 for gravity. And then we know that because friction is going to take energy out of the system, this negative is just really showing us the direction that force is acting on, so it's not really important. So then when you do the math, you find that the coefficient of kinetic friction is 0.407 for the coefficient of kinetic friction. And that's how you solve the problem.